Okay, now am I audible to everyone?
Yes, sir.
Yes. Okay. Okay, so we have ended over here. Now we have to start the part B. K can also be synthesized from phenol. Okay. Figure 4.4 shows several reactions of phenol. Okay. Here in reaction 1, we are using a sodium metal. So what would be the product? It would be a sodium phenoxide where the H of OH is substituted by a sodium metal. Here we are using the bromine in N. And if you recall, with excess bromine, what would happen? That OH is electron donating in nature. So it is going to substitute the bromine to the, if there is an excess bromine, so bromine to the 2, 4, and 6 positions. And in reaction 3, so reaction 1 is basically an acid-base reaction. Reaction 2 is basically electrophilic substitution. And if we look at reaction 3, we have added sodium hydroxide, then carbon dioxide and sulfuric acid. Okay. Let's see, are we going to discuss this reaction 3 in a while? Okay. So write an equation for the formula M in reaction 1. Okay. So we have to write the equation for this. If we write the molecular formula of phenol, it is basically C6H5OH reacting with sodium metal, forming C6H5ONA and a hydrogen gas. And to balance the equation, I have to put half over here. Okay. Draw the N, the product of reaction 2. So we have already drawn it over here. So let's draw this, that a benzene ring over here. Having a OH, and with respect to that OH, that the second carbon, fourth carbon, and sixth carbon have a Br. Okay. Now in the next part, they are asking explain why phenol is weaker acid than K. Okay. First, let's discuss about K. Here you have got getting K. It means what would happen when we have added NaOH to a phenol. First, that phenol is actually converted into this thing. And then when we have added a carbon dioxide to this is converted into this thing. And then when we have added a sulfuric acid to this would form. Is this understandable? So see, we have our two groups in K. So there are actually three reactions occurring. First one, this one with NaOH it's an acid-base reaction. Then when we added a carbon dioxide, it is electrophilic substitution, and when then we added a sulfuric acid, again it's an acid-base reaction. So here we have added NaOH, then we have added carbon dioxide, and then we have added sulfuric acid over here. Okay, so they are asking why it is a more stronger acid uh, than the phenol. So the reason is behind this that over here, if we talk about this group, here there is a this carbonyl oxygen which withdraws electron from here. Sorry, the sign is wrong. It withdraws electron from here towards itself due to this bonds get weaker and H positive is easily released.
सर ये रिएक्शन 2 में जो है ये ब्रोमिनेशन नहीं होगा इलेक्ट्रोफिलिक सब्स्टिट्यूशन हो जाए
Sorry,
ये ब्रोमिनेशन नहीं हो रहा रिएक्शन 2 में सर
reaction 2,
जी जी ब्रोमिनेशन नहीं हो रहा इसमें
it's why bromination? Where is bromine?
जी सर ये जो फिनोमिना ब्रोमिनेशन होता है इलेक्ट्रोफिलिक सब्स्टिट्यूशन तो नहीं होगी ना इसमें
See, we can actually figuring out this thing from here, from the K, that in K there is one more substitution, and that is the substitution of this carbon over here. So this carbon is actually coming from this carbon dioxide. So here, by adding carbon dioxide, this group is being substituted onto
मैं
this
रिएक्शन 2 की
phenol.
बात कर रहा हूँ मैं रिएक्शन 2 की बात कर रहा हूँ
Yes, it's electrophilic okay, it's electrophilic substitution. We named it bromination, but bromination is not the type.
ओके ठीक है सर सही सही थैंक यू
Bromination is not the type of the reaction. It is named as bromination because bromine is being substituted. Bromine is substituting the hydrogens. Okay, so that okay. Let me do one thing. We have a phenol over here, and we have a K over here. In K, we have this carboxylic acid group which is bonded to a phenol. Oh, benzene ring. So I can write that K is stronger acid than phenol as it I think it's better, as it donates H positive ions more readily than phenol. This is obvious. If one is a more stronger, then it means it releases or it donates the H positive ions more readily. It is because that C double bond O is bonded to OH, and that C double bond O is electron withdrawing which makes COO negative more stable than phenoxide ion. And that's why it gets the K is more stronger acid and this phenol is a weaker acid relatively. Is this understandable to everyone? Yes.
Yes, sir.
Okay. Now, phenol and benzene both react with nitric acid as shown. Okay. For phenol, if you see, we are using dilute nitric acid, and with benzene, we are using concentrated nitric acid and concentrated sulfuric acid. Further, let me recall you that this reaction is occurring at room temperature pressure conditions. And here we need a temperature of around 55 degrees Celsius. Okay. So explain why the reagents and conditions for these two reagents are different. Okay. So actually what would happen in phenol, the oxygen bonded to benzene actually induces its electron or overlaps its p orbital with pi system. As a result, the electron charge density increases in benzene ring. Hence, it can attract electrophile more readily than benzene. Actually, when it overlaps its p orbital, so as a result, it induces its electron towards the benzene ring, due to which there are more electrons in this pi system, and as a result, its electron density increases, so it can attract the electrophile more readily as compared to this benzene molecule, and that's why we do not need any sulfuric acid, which is we are using as a catalyst in the second reaction. There is no catalysis needed. Is this understandable to everyone?
Yes, sir.
Okay. Now we are going to start question number 5. Okay, so we have a 2-chloropropanoic acid. Here it is used in many chemical synthesis. An equilibrium is set up when 2-chloropropanoic acid is added to a water. Write an equation for this equilibrium. So in this equilibrium, we normally write the dissociation of an acid as you do with the normal acid. So this H is basically the H that is released by any carboxylic acid. So we would write the equation. That's first we would write the formula for a 2-chloropropanoic acid, and hence it's a weak acid. So you would use a reversible arrow. Then you would repeat the formula, but without the last hydrogen. Instead, you put a negative charge over here and you put a H positive on. So that would be the equilibrium or the dissociation equation for a carboxylic acid. For any carboxylic acid, you can write the equation in this manner only. Now, 0.15 mole of 2-chloropropanoic acid dissolved in 250 centimeter cube of distilled water to produce a solution of pH 1.51. Okay, they have provided you the pH. Now, what they are asking? They are asking you to calculate the pKa. Okay. So, if you recall, if you have to find the pKa, that pKa is equals to minus log Ka, and if you have to find the Ka is actually equals to concentration of hydrogen ions square over concentration of acid, and we are given with the pH. So if you have given with the pH and you have to find the concentration of H positive ion, it would be like concentration of H positive ion is equals to 10 raised to the power minus pH, and we don't know the concentration. So for finding the concentration of an acid, we are provided with the moles divided by the volume that must be in decimeter cube. So these are the expressions that we are going to use in this order. First, I would use this one to find the concentration of acid. Then I would use this one to find the concentration of hydrogen ions. Then I would use this one to find the value of Ka. And then I would use this one to find pKa. Is this understandable to everyone? So let's find the concentration of an acid, that is 2-chloropropanoic acid. It would be equal to 0.150 divided by 250 over 1000. Can anybody tell me the answer? Yes.
0.6.
0.6, and there is no other digit afterwards.
No.
So okay, so 0.060 mole per dm cube. This is the concentration of this acid. Okay, then we have to find the concentration of hydrogen ions, which is equals to 10 raised to the power minus pH, and minus pH value is 1.51. So can anybody calculate it and tell me the answer? Okay, Sarah, 0.0309. Now I've got these two values. Now I would find the Ka. Ka is equals to 0.309 square over 0.60. Yes, what is the answer over here? Okay. Thank you. 0.0309. Yes, Ravisha, if you will write combination, it will be wrong for the previous one. Yes, can anybody tell me the answer?
Sir, 1.59 into 10 to the power 3.
1.59
into 10 to the power negative 3.
negative 3. Now for pKa, I would take minus log to the base 10 of this value 1.59 exponent minus 3. Yes, 0.2, sorry, 2.7986. So if I turns into three significant figures, it would be 2.80. So this is the answer. Okay. An equal concentration of aqueous propanoic acid has a pH 2.55. Explain the difference in the pH of the solution of equal concentration of 2-chloromethanoic acid and the propanoic acid. So its pH is 1.51 and its pH is 2.55. Basically, if you recall, pH is the measure of the degree of the hydrogen ions present in the solution. So if its pH is greater, which means there are lesser hydrogen ions in the solution, hence it's a weaker acid. Explain the difference in the pH. Okay. So the difference suggests us that uh, that this is stronger acid than propanoic acid it is because this 2-chloropropanoic acid dissociates more in water or in its aqueous solution as chlorine is electron withdrawing group makes OH bond more weaker than in propanoic acid. Yes, is this reason is understandable to everyone? If anybody have any doubt, kindly ask. Okay. When 2-chloropropanoic acid reacts with aqueous ammonia, alanine forms. And if you recall, here if you see, there is a carboxylic acid group in it, and there is a amine group in it. So this alanine is basically an amino acid. Okay, they have mentioned that it's an amino acid and its isoelectric point is 6.1. What does this isoelectric point is 6.1? That 6.1 is a pH where the net charge on alanine is 0, or there is no net charge on alanine at this pH. Okay, so what does this are asking for? That what is mean by the isoelectric point? So it's simple. That's what I have just mentioned. That it is the pH where a molecule have no net charge. Is this understandable? Okay. Now, give the structural formula of alanine at pH 2. So, at pH 6.1, it have a no net charge, which means it is actually existing as a Zwitter ion. So, what would be the Zwitter ion of this alanine, that in which the carboxylic acid part is actually released its hydrogen ion, and the amine part is actually accepted that hydrogen ion, and see there is a one positive one and a negative one, which makes it a neutral. Okay, so there is no net charge on it. Now and this would be at pH 6.1. Its structure would be like this, and here they are asking you the structure at pH 2. So if we are talking about pH 2, it means that the solution would be more acidic because it is the lower pH than pH 6.1, which means there are more hydrogen ions in the solution. So if there are excess of hydrogen ions in the solution, then what would happen? That the carboxylic acid part, which have a negative charge, accept those hydrogen ions, turning into a COOH group, and the rest of the molecule stays the same. So now it becomes a positively charged ion at pH 2. So that would be its pH, it's the structure at pH 2, and that is the structure of that amino acid at pH 6.1. Is this clear to everyone? So they are asking for the structure. So I would write that NH3 positive, CH, CH3, and COOH. Is this clear? Okay. Now next part. Alanine exists as a pair of optical isomers. The structure of one optical isomer is shown in figure 5.2. Draw the three-dimensional structure of the other optical isomer of alanine. So it would be very easy. You have to just draw its mirror image. So place a carbon in the center, the one bond above, CH3, the one bond going away, NH2, the one bold bond having COOH, and having one dotted bond, NH. Is this clear?
Yes, sir. So in part 2, if it's acidic at pH 2, so like why it is gaining more hydrogen?
Sorry, can you repeat your question?
If it's like more acidic at pH 2, why are we gaining more hydrogen?
Because see, simply if you look at this oxygen, this oxygen have a negative charge, which means it have a 3 lone pairs, right?
Right.
So this oxygen have an ability to accept the hydrogens. And they have mentioned that it's isoelectric point. So obviously, if the pH would get lower than this one, then it means there are excessive hydrogen ions which can be accepted by this one. So in the same way, if examiner have given you that same pH and ask you to show the structure at, for example, pH, let's suppose 7. So it means that at pH 7, there would be more hydroxide ions. So what would happen? That this part actually come into action and hydrogen is being released. So at above its isoelectric point, it would become NH2 by releasing the hydrogen ion, which actually bonds with the excess hydroxide to form water, and we have this structure, a negatively charged ion.
Right, sir. Thank you.
So that is the same thing you have to remember when, if you go above the isoelectric point of any amino acid, then the NH3 positive group releases the hydrogen ion and it becomes neutral and it stays the same. But when we go at the lower pH to the isoelectric point, then this part accepts the hydrogen, becomes neutral, and this part remains the same. Is this clear?
Yes, sir.
Okay. Now, polymer C forms from the reaction between alanine and 4-aminobutanoic acid, and here we have the structure. Draw the repeat unit of C, and C is what? C is a polymer. The functional group formed should be displayed. It means you have to show the okay. So if I will draw alanine over here, for example, alanine have a carboxylic acid on one end. On the other end, it have a NH2 and one side H and one side CH3. That is alanine. Okay. Now, 4-aminobutanoic acid, if I would draw it, there is a nitrogen over here with the 2 hydrogens. Then we have CH2, 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 and C double bond O, OH. And that is 4-aminobutanoic acid. So we have a 2 different monomers, and we have to show the repeat unit. So what would happen here? We have a one carboxylic acid group and one amine group. So the OH from the carboxylic acid group and the H from the amine group is removed. From here and from here as well. Then what is left behind? This part from the alanine and this part from the 4-aminobutanoic acid. So one hydrogen is released from here and one hydrogen is released from here. So this nitrogen and this carbon going to bond with each other. Here we have a one empty bond and here we have a one empty bond. So this is how one repeat unit is actually made. Is it clear to everyone?
Yes, sir.
Okay.
सर 4 अमाइनो ब्यूटानाइक एसिड का स्ट्रक्चर थोड़ा वो आपने CH2 3 बार नहीं बनाया.
See, there are three CH2. How? 1, 2, 3. And 4 one is a carboxylic acid.
Oh, okay, sir.
Okay, now what they are asking? State the type of polymerization shown in B4. So as the what gas Taha, good. Water molecules are being released, so it is condensation polymerization. Scientists are investigating C as a replacement of polypropylene in packaging. Suggest an advantage of using C instead of polypropylene. Okay. Yeah, can anybody suggest any advantage of using C instead of polypropylene?
Sir, polypropylene can easily compound instead we are using a propylene is easily biodegradable and can easily be broken down.
Why? Yeah.
It can be hydrolyzed
Why? What is the reason?
because it has an amide linkage.
Yeah, it's an amide linkage, very good. So it's a polar one. So it can be biodegradable as well as it can be easily hydrolyzed. So C is biodegradable and you can also write C hydrolyzed easily. Okay, now C part. A student studies the reaction of 2-chloropropanoic acid with aqueous ammonia to determine the reaction mechanism. Okay. The student finds when 2-chloropropanoic acid and ammonia are added in 1:1 stoichiometric ratio, the conjugate acid and base of the reactants are quickly formed. Okay. So if you see, this is an acid and its conjugate base is this one, and it's a base and its conjugate acid is this one. Identify the conjugate acid base pair in reaction 1. Okay. So we just figure it out. So we have to write over here that first pair would be CH3, CHCl, COOH, and its conjugate base would be CH3, CHCl, COO negative. The second pair would be NH3 and ammonium NH4 positive. In an excess of ammonia, 2-chloropropanoate undergoes nucleophilic substitution reaction. Okay, and here we have the equation. If you see, this chlorine over here is being substituted by ammonia and turns into amine, and we have these ions. A student investigates the rate of reaction 2. Okay, this is reaction 2. Student mixes 2-chloropropanoate ion with a large excess of ammonia. The graph in figure 5.3 shows the result obtained. Okay. So here we have a change in the concentration of 2-chloropropanoate with respect to time. Okay. Use the graph in figure 5.3 to show that reaction 2 is first order with respect to 2-chloropropanoate ion. Okay. So what would we do for this? It's a concentration time graph. So what we would do, we would go for the half-life, and if, yeah, very good, Taha, and if the half-lives are constant, then it indicates that it's a first order. So if you look at this, what would be the value? It's 0.021, right? So the half would be 0.0, this would be the half. So I take the half of the initial concentration and then check the time. So how much time is over here? 500 seconds. So the first half-life is of 500 seconds, right? Now the next half-life, it would be the 1/4 box. So if you see, again, the second half-life from the start, again, it's a 500 seconds, right? So we got two consecutive half-lives, and both are two successive half-lives are same. So it's a first order. So we would mention over here that the consecutive half-lives are same, that is half-life is 500 seconds, hence its first order with respect to the concentration of 2-chloro-propanoidine. Okay. Now, explain why a large excess of ammonia needs to be used in order to obtain the result in figure 5.2, 5.3. In one of the previously then past papers, there is this kind of a question. So, can anybody answer this one? Why there is a large excess ammonia?
So it doesn't affect the rate and remains constant.
Yeah, because good, because when we use a very large excess of one reactant, so if it is obviously it is also reacting during the course of the reaction, but that the decrease in its concentration is not significant. So we can say that it stays almost constant and does not affect the rate. So the concentration of ammonia remains almost same. You can say that no significant change because it's in very large excess. Hence, does not affect the rate of reaction. Okay. Now, the student measures the effect of changing the concentration of ammonia on the rate of reaction 2. Okay. Use the information in table 5.1 and C2. Okay. In C2, we got that the order with respect to 2-chloropropanoate is 1. Determine whether the nucleophilic substitution reaction proceeds via SN1 and SN2 mechanism. Oh, that's good. So if you recall, we have all discussed these two in AS level. In SN2, if you recall the SN2 mechanism, it's a single step mechanism where a intermediate is a transition state having a carbon, 5 bonds of a carbon, and it is a two-step mechanism where first the carbocation is formed in SN1 and then the nucleophile attacks on that carbocation. Okay, so if you see, these are ammonia. Isn't it changed by 1.5? Yes, the change in the concentration is 1.5. Now, what would be the change in the rate? How could you figure it out? Dividing the this with this one. Yes. Is it also 1.5? Can
Yes.
anybody verify?
Say 1.5.
So, if you see in reaction 2, when compared with the reaction 1, the concentration of ammonia is increased by the factor of 1.5, and hence the initial rate is also, increased by the factor of 1.5. So it means that it is also present in rate determining step. In rate determining step. So it means it is basically then the SN2 mechanism, because it's a single step mechanism, and in this one, when the halogenoalkane and the nucleophile both are present in the rate determining step. Okay, but if we would find from this calculation that the change in the concentration of ammonia does not affecting the rate, then it would be SN1, because in SN1, in the rate determining step, there is no nucleophile, there is only halogenoalkane present in it. So we would write over here that as the concentration of ammonia is increased by 1.5 times the rate of reaction also increased by 1.5 times, right? So with the help of C2, what we have figured out, so I can write with respect to the concentration of 2-chloropropanoate ion, its first order, and here we have figured it out that with respect to the concentration of ammonia, its first order as well. Hence, its proceed via SN2 mechanism. Is this understandable to everyone? Yes. Is it clear? Okay, you would see over here where it is. Let me show you. We have discussed this in our lectures as well, if I'm not wrong. See, here the reaction is proceeded via SN2 because it's a primary halogenoalkane, and if the reaction is proceeded via SN2, then both the nucleophile and the halogenoalkane have a first order. That's why they both are present in the rate equation. That's why it's SN2. And when then we have this halogenoalkane, the tertiary one, the reaction proceed via SN1. And in SN1, this is the slow step or the rate determining step where the halogenoalkane is present. So the it's first order with respect to halogenoalkane only, not with respect to nucleophile. So if we would observe this output in our question, then we would suggest that the reaction is proceeded via SN1 mechanism. But here we got actually this output that the order with respect to halogenoalkane and the order with respect to nucleophile is first. That's why we have suggested that it's an SN2 mechanism. Yeah, is this clear now? So you can go over the notes as well. Now, next part. Describe the effect of an increase in temperature on the rate of reaction of these. Explain your answer. Okay. This part I think comes from the AS, that an increase in temperature increases the proportion of molecules having energy equal to or greater than activation energy. As a result, frequency of successful collisions or effective collisions increases. Hence, the rate of reaction increases. Okay. When an excess of 2-chloropropanoate is used, further substitution reaction occur. One product has the formula of C6H9NO4 negative. Oh, okay. So this is the structure. Yes, can anyone do this? What they are saying, when there is an excess of this molecule, then this would happen. Okay, let me help you think. Initially, I have this structure, and we have used ammonia. And due to the use of ammonia, this chlorine is substituted by NH2, and we got this. But what they are saying that this is in excess now, right? And due to its excessness, further substitution would occur. So what it could be the structure. So think, if it's in excess, it's a ammonia where the hydrogen of ammonia is substituted and the nitrogen is bonded with the carbon. So same thing happen over here. That see, now we are left with the two hydrogens. What would happen if the first product is in excess? So the hydrogen and the chlorine from here, let me remove these two, removed, and when this is removed, this one is going to bond with this one. So the structure would be CH3, CH, C double O negative. Here we have an N, a hydrogen, and to this N, the CH of the another molecule would be bonded, C double O negative and CH3. Now, identify its molecular formula. C, H, N, and O. 1, 2, 3, 4, 5, 6. 3, 3, 4, 6, 7, 8, 9. 9 hydrogens. One nitrogen and 4 oxygens. So C and 2 minus charge. So see, we got the structure. Is this understandable to everyone?
Yes, sir.
So this is the answer. This is the structure of this one. If anybody have any doubt, kindly ask. Okay. Now, the question number 6, the last one. Lidocaine is used as an anesthetic. A synthesis of lidocaine is shown in figure 6.1. Okay, here you go. So if you see over here, what would happen? The H from here and the this chlorine is being removed, minus HCl. Just give me a minute, please. Okay. Yeah. So which kind of reaction is reaction 1? Condensation reaction, or you can call it addition elimination as well. That you have studied in carboxylic acid derivative. Now, if you see reaction 2, the same thing happened. The hydrogen from here and the Cl from here is removed, and this nitrogen is bonded to this carbon, giving you this lidocaine. Is this understandable to everyone? First, what would happening over here? If you see this chlorine and one hydrogen from this is removed, and due to this bond is formed and these two molecules join. Then In the second reaction, this chlorine and this hydrogen are being removed, and the same nitrogen bonded to that chlorine, and that is the bond over here, or that carbon, not chlorine, because chlorine is removed. Yeah, is this understandable? W can be formed by reacting OHCH2COOH with an excess of SOCl2. Okay, here we have an alcohol and here we have an carboxylic acid. Write an equation for this reaction. So I think this kind of equation we did in the previous paper as well. So that when we use SOCl2, or beside SOCl2 we use PCl3 or PCl5 in any of these reagents, the OH of a carboxylic acid and the OH of alcohol is substituted and the chlorine takes their place. So same would occur over here, that chlorine substitute the alcohol's OH forming CHOH bonded to CH2, then COCl, that OH is also going to be substituted. So beside this, we are going to get a sulfur dioxide gas and HCl. So to balance this equation, we have to put 2 over here and 2 over here. Okay. After W and X have reacted together, an excess of this ion is added to the reaction mixture. Suggest why. Okay, these are the W and X, and what they are saying that when these two are mixed together, an excess of this ion is added to the reaction mixture. Yes, can anybody identify the reason?
Sir, I think it is added to react with the compound formed HCl formed after this reaction.
Sir, madam.
During this
Sir.
reaction, what other product we are forming? We are getting
HCl, sir.
during this
HCl.
HCl. So HCl is an acid, right? So there is a possibility then these two undergo reaction. So to prevent this reaction being happening, if we add CH3COO negative over here, so it combines with this HCl, and as a result, we would get this, but stronger acid is being consumed along with the spectator ions only in the solution. So that's why we have added this. So W and X have reacted together, and so you just write that and excess of is added. 1 minute. Okay. To, or you can say just to remove acidic byproducts that are formed. Is this clear? Yes. Okay. The reaction of W and X, if you recall, this one is a W and this one is an X. Reaction 1 follows an addition elimination mechanism. Okay. Complete the mechanism for reaction of W X. Include all relevant curly arrows, lone pairs. These are the most important things in the mechanism. Curly arrows, lone pair, soft electrons, charges, partial charges. Use AR and H to represent X. Okay. So what would happen over here? That this chlorine is being substituted, if you recall. So we would have a lone pair over here. This carbon is partial positive and the oxygen is partial negative. So from this lone pair, we made a curly arrow to this carbon and another curly arrow from this bond to the oxygen. As a result, the intermediate that is formed over here is actually Cl. Here we got this and H2 bonded. I'm now showing both the H individually, and here we got an O negative with a lone pair. So what would happen in the next stage? That it introduces its lone pair again over here. At the same time, this chlorine break this bond heterolytically by taking away the pair of electron, and as a result, here we got a double bond. Here we have a Cl. Here we get, okay, 1 minute. I forgot one thing. As this nitrogen forms 4 bonds now, so it have a positive charge. So in the meanwhile, when this would be occurring, this nitrogen also breaks the bond heterolytically from the hydrogen. So we are left with the one H bonded to a nitrogen and the arene ring over here. So that is our product, and the H and Cl are removed, which form HCl. So this is the mechanism. You can find these mechanisms in the carboxylic acid derivatives. If you see over here, see, this is the same mechanism with the water and with the amine. See here, it's with the ammonia, and here with the amine. See here we have a CH3, and what the examiner did, beside the CH3, examiner gives you an AR over here. Otherwise, the rest of the mechanism is same. Okay. Now the next part. I think we are just left with 1 or 2 parts. This reacts with Y in reaction 2. Okay, explain why this can act as a nucleophile. So it's very simple. It's a nucleophile because it have a lone pair. And it donates a lone pair. Nitrogen have lone pair of electron to donate to Y. That's why. Is this clear? Now, E part, it's from chromatography. The purity of lidocaine can be checked using thin layer chromatography. Ethyl ethanoate is used as a solvent. The RF value of X and lidocaine are given in the table 6.1. Okay, so it's the solvent, and X have a RF value of 0.49 and lidocaine have a value of 0.71. So what it indicates that it is less soluble in the mobile phase, that is ethyl ethanoate, and it is more soluble in the mobile phase, that is ethyl ethanoate. So we got their solubilities in ethyl ethanoate. Identify the substance used as the mobile and stationary phase in the thin layer chromatography. So ethyl ethanoate is the solvent. So whatever is the solvent is the always the mobile phase. Okay. So here we would write ethyl ethanoate. Then the stationary phase. It's a thin layer chromatography, and we have studied in thin layer chromatography the stationary phase is a silica or alumina. Silica is SiO2 or alumina is Al2O3. So these can be your these are actually the stationary phase in the chromatography. So you just write either the formula or the name of any one of these. Now, okay, describe how the RF value can be calculated. I think you all are familiar because you have studied in your IGCSEs and in O levels as well. So RF value is, it is calculated yes, it is calculated by dividing distance traveled by solute from distance traveled by solvent. Suggest why the RF value of X is less than that for lidocaine. So that's what we have already discussed, that it is lidocaine is more soluble and X is less soluble in ethyl ethanoate. X is less soluble in mobile phase or ethyl ethanoate. Is this clear to everyone? Or further, you can write as this thing that it is, if it's less soluble in mobile phase, then it is actually it have a more affinity and it is more attracted towards the the stationary phase. That's why its movement is slower. That's why its value is smaller. So X is more attracted towards stationary phase.
सर ये इसलिए कि X से ज़्यादा पोलर है.
Yes, it's obviously because these are the polar ones. So X would be more polar. That's why.
सर ये वाटर और अल्कोहल जो किसका इस्तेमाल करता है, कौन सी क्रोमेटोग्राफी में होता है?
So that was in the paper chromatography, which was previously in our syllabus, but now it is eliminated.
Understood.
Okay. If the proton NMR spectrum of lidocaine is shown, here you have the structure of lidocaine, and here it's a NMR spectrum. Okay, here we are provided with the values. Okay, first what they are asking, name the splitting pattern at 2.6 and 1.1. So at 2.6, if you see, there are 4 signals, which means it's a quartet. And at 1.1, there are 3 signals, which means it's a triplet. Now, the relative peak area of peaks at 3.0, 2.3 is 1:3 respectively. Okay, 1:3 respectively. Identify protons in the proton NMR spectrum of lidocaine that are responsible for the peaks at the following chemical shifts. Okay. So, first talk about 7.1. If you see over here, 7.1, it lies in this range, which means a proton attached to an aromatic ring, right? So here I would write that proton attached to aromatic ring. Now we have one at 3 and one at 2.3. So these are the protons which are giving a signal at 7.1. Sorry, yeah, these are the protons. Now at 2.3, if you see, there is a singlet. Okay, so it means on their neighbor carbon there is a no proton, so it's a singlet. So if you see this carbon have a 2 hydrogens, right? And to its neighbor, there is a nitrogen over here and there is a carbonyl. So there are no protons on the neighbor carbon. And let me see over here. And it is next to carbonyl. So if you see alkyl next to carbonyl, the value is 2.2 to 3.0 and our value is 2.3. So it means it could be a protons of an alkyl. No, not this one. This one. Alkyl next to carbonyl, which would be like this CH2 bonded to C double bond O. So the signals of these 2 protons. Okay, now at 3.0. No, 1 minute. Okay, see over here we have this one as well. Oh, that's good. Just wait. Now think. If you see over here, this is also a singlet and this one is a singlet. So it means in their neighbor there are no protons. But if you look at the height is telling me, I actually overlooked initially, that height is telling me that this signal have a more hydrogens and this signal have a less hydrogens. And we got the area of these 2 heights. If you see, that is, they have mentioned over here, that is 1:3. See, 1:, no. For the signal at chemical shift 3.0, it's 1 and it's At 2.3, it's 3. So these two are singlet. Now, if you see over here, there are also 3 hydrogens over here and 3 hydrogens over here. So these 6 hydrogens are also giving a signal which would be a singlet, because on their neighbor carbon there is no hydrogen. See this carbon and this carbon. And you look at these hydrogens, these 2 hydrogens are also going to give you a singlet, because on one side there is a nitrogen and on the other side there is a carbonyl, so you are not going to get a there is no hydrogen on the neighbor one, so there is no splitting over here. Is this understandable to everyone? Yes. So if you relate these hydrogens, that 2 hydrogens and 6 hydrogens, so what would be the ratio? That is 1:3, right? And that is the ratio that they have provided. So it means that at chemical shift 2.3, I am getting the signals of these two. And the chemical shift 3, I am getting the signal of these 2 purple hydrogens. So basically at 2.3 is this one, because it is alkyl next to aromatic ring, and 3.0 is this one because alkyl next to C double bond O. The ratio of their heights help us to identify. So over here, alkyl next to carbonyl, and over here alkyl next to aromatic ring. Is this clear?
Sir, apart from the ratio, can we also consider that it's more further from the oxygen?
Yeah, but this is the this is the hint that is provided to you by the examiner.
Right.
So from this we can easily get to know which one is of a which signal is representing which hydrogens from the structure. Now the last part, predict the number of peaks in carbon 13 NMR spectrum of lidocaine. So we have to figure out how many different types of carbons are over here. So let me draw the structure over here. 1, 2, 3, 4, 5, 6. Here I have a 1 carbon, here I have a 1 carbon, nitrogen, then C double bond O, then a carbon, then nitrogen, where we have a 2 different carbons. Okay, so this carbon have a completely different signal. This one is different. If you see, these two are actually similar. These two are going to be similar. These two are going to be similar. This one is different. No. Okay. So these two are going to be different one. These two are going to show you a different color or different chemical environment. And This one is going to show you a different one. So see how many different types of carbon we are getting over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 different types of carbon that we are getting over here. So there would be 9 signals over here. Is this understandable? So here we have ended this paper, and hope inshallah we are going to do another class at 12 midnight, and where we are going to start the summer May-June of 2022 paper. Okay, so take care everyone. Allah Hafiz.